When measuring spin, I can use a magnet oriented to the z-axis, which is perpendicular to the beam of silver atoms, or I can use an x-axis magnet, which is also perpendicular to the beam of silver atoms and perpendicular to the z-axis, or I can use a y-axis magnet, and that would be parallel to the beam of silver atoms but perpendicular to the z and the x-axis. So it's hard to draw something like that, so I put this little circle with a cross in it to indicate that it's going into the page, if you want to think about it that way. No matter which magnet I use, I'm going to get two outcomes. I use this plus sign for aligned and the minus sign for not aligned. These are the only two results, regardless of whether we're doing a z-axis, an x-axis, or a y-axis. The y-axis doesn't cause a deflection, it causes an acceleration or a deceleration of the atom itself, which is extremely difficult to measure. Here's a couple facts from the experiments. If I take a aligned atom, which went through the z-axis magnet and it came out measuring as aligned, I can keep measuring that with the z-oriented magnet and I always get plus. I never get minus. So if I prepare it with z and measure it with z, then I'm always going to get the alignment. So we've got certainty there. I have the same situation, an aligned atom prepared with z, meaning it goes past the z magnet, but then it's measured by the x magnet. And what experiments show is that if these x and z are actually perpendicular, then we get a 50-50 spread of some of them are aligned, some of them are not aligned. Now a third statement. If I have an aligned atom that came from a z magnet measurement, and I measure it with an x magnet, and I select one of the samples that was aligned with the x magnet, if I then measure that with z, it's not always aligned. So somehow just measuring it with the x magnet has not really changed the spin property, but it changes the basis upon which that measurement was made. So it actually has an effect. So the big deal is that by measuring it with z, and as long as I always measure it with z, I'll always get that same result. If I switch basis measurements in between times, then that's going to affect the probability of what the outcome is. What I just went over here is so important that I can't describe it properly. But think about it. First of all, measurements take a continuous state and create a fixed value, which is an eigenstate. And that eigenstate has a lot to do with quantization of the world. If you measure something, you're going to get an eigenstate. You don't have a choice on that. And that eigenstate is described by the coordinate system that you're using. This gets rougher because we're getting closer to what the reality is. And that the idea that you can measure something and not affect it is an idea that comes from your experience. When you look at something and record what's going on in your head, you're thinking, oh, I'm outside that object. There's no way I'm tied in with that object. But we're going to have to change that thinking, because the thinking is very fundamental about the idea of measurement, outcomes, eigenvectors, quantization, and we haven't even hit probabilities. Probabilities is coming up next.